In this video, we're going to start to look at some more applications of derivatives. And first, we're going to examine functions and look at their maxima and minima. And we'll call this conglomerate the extrema. So we're going to look at both absolute and relative extrema. So I want you to imagine walking along a hilly terrain. And as you walk through, you see that there are going to be some high points and some low points as you walk through. And each of these points, when you're on a point that is relatively higher than all the points around that, we call it a high point, and this would be a relative max. And when you come across any of those low points that are relatively the lowest point in the points around it, we call that the relative min. Well, we're going to treat functions the same way and say that as functions move up and down, they have these relative maximum points and these relative minimum points. They're called relative because they're the highest point of the points close to them, relative to that point. But they might not be the highest high or the lowest low. They just are a relative max or a relative min. To have the highest high, the very highest point that we get, that would be the absolute maximum, and the very lowest low would be the absolute minimum. So we define absolute extrema by saying that if we let f be defined on a set D containing some point C, and if f of C is greater than f of x for every x in D, then f has an absolute maximum value of f of C on D at C. So that's saying that if that is the highest high point, then that f of C is the absolute maximum. As long as it's higher than all other f of x, it's the absolute max. And we can say the same thing, that if f of C is less than or equal to f of x for every x in D, then f has an absolute minimum value of f of C on D at C. Absolute extreme values refer to either the absolute maximum or the absolute minimum. So when we talk about the adjective absolute, we mean that is the highest high and the lowest low. Nowhere else on the function does it get any higher than that maximum, and nowhere else on the function does it get any lower. Let's take a look at this function y equals x squared. And if we initially look at the function on the interval of all values of x, we see that it first off has no absolute max because it goes off to infinity. Both in the left and right direction, it goes off to positive infinity. So there is no maximum. There's no absolute maximum. And there is an absolute minimum in that at its vertex, that's when it reaches its lowest point, and that's at x equals 0, it has an absolute minimum of 0. However, let's look at the same function, but let's change the interval and look at it from 0 to 2. And on the interval from 0 to 2, this function does have an absolute max in that at its endpoint, that is its maximum value of 4 at x equals 2. And at its other endpoint, we have our absolute minimum. And we say, and we're going to get into this description a little more later, but this is true because this is an increasing function. This function is increasing over the interval from 0 to 2. So its endpoints are its minimum and max. Continuing with this same function, but now let's look on the open interval of 0 to 2. We have no absolute minimum because we have an open circle here. All right, well, you say we're not including that point, so we can't have a minimum because what is our value there? What's our x value? It's not 0. We're not defined at x equals 0. And so we say that there is no absolute minimum on this interval because we have an open endpoint and our function is continuing to decrease as it approaches that endpoint. However, we do have a maximum because we are defined up here at x equals 2, and so we have an absolute max of 4 at x equal to 2. Now if we look at the same function for a fourth time, but both the 0 and 2 are open-ended on our interval, then there's no absolute max, no absolute min, for the same reason that we didn't have a minimum in part C. Looking at that first example, you may start to think that, well, if we have a closed interval, then we're going to have an absolute max and min. Well, that is not always the case, and this figure shows an example of that. if we have a closed interval, so we're looking at this function on the left here from 0 to 1, and we're including both 0 and 1, so we're on the interval, the closed interval from 0 to 1, we see that we have an absolute minimum value of 0 at two different x values, but there is no absolute max because the function goes off to an open circle. Even though we're defined at x equals 1, we're undefined where we see our highest y values. And so we don't know what y value we approach. We know our limit as it approaches 1, it looks like we're approaching a y value of 1, but we are not defined there at that point. So we cannot say that we have an absolute maximum. This other function on the right is another example. We have an absolute minimum down here, but if we look what's our highest y value, well, it's not this point here because we are higher up here, but we're undefined at that point, and so therefore we have no absolute maximum. So what do these two graphs have in common? Even though they're closed intervals, they have something in common in that there's a break, and we say that those functions are not continuous. This discontinuity is what's causing that disconnect between closed interval, meaning there should be an absolute max and min. This then leads us into the extreme value theorem, and we often shorten this to the EVT, extreme value theorem. And it states that a function that is continuous, so if we have a continuous function on a closed interval, it has an absolute maximum value and an absolute minimum value on that interval. So if a function is continuous on a closed interval, there must be a max and there must be a min. If it's not continuous, then all bets are off. It could have a max, it could have a min, it might have one or not the other, it might have both, but we can't say for sure. What we can say for sure that if a function is continuous on a closed interval, then there is a max and there is a min. One more example of this, we have a continuous function y equals f of x here on the left, and we're on the interval a to b, and we see that there is a max here at a, and we have a minimum at c. And because it's continuous, there has to be those 2 points, one being a maximum point, one being a minimum point. Conversely, over here on our other example here of g of x, we see that we have this disconnect, so there is no max, and we're on an open interval at our lowest points, so that means there's no min. Let's look at a function that is continuous and defined on the interval from a to b, and we see that we have several high and low points as we look through this function. And we see that at a we have our lowest low point, and we say that that is the absolute minimum, and there's no smaller value on the interval for f. F is never smaller than at that point. And we can look as we go along, we see that the highest high point is defined over here at e because no other value is higher than that high point. However, we do have two other points of concern here. We have this high point at C and a low point at D. We call those local extrema or relative extrema. Okay, local and relative are synonymous. We'll use them interchangeably. And this is a local maximum because there's no greater value of f nearby. That is our highest point around f in this area. There's nothing higher, and there's nothing lower around this area. So we call those relative or local extrema. One thing to mention here is that at the endpoints A and B, these will never be local extrema or relative extrema. However, they could be absolute extrema because this is the lowest point at which our function goes on our interval here. And so we say it's the absolute minimum. If we have the highest point, then it's the absolute maximum. However, here at B, we can't say whether this is going to be a local minimum because we don't know what's happening to the right of B. And so we can't assume that it's going to reach a low point at B and then continue back up. And so we don't call it anything. If it's the absolute maximum or minimum, we can classify it as that, but we won't classify endpoints as local extrema. The formal definition of local maximum and minimum values states that suppose we have C that is an interior point of the interval I on which f is defined, and if f of c is greater than or equal to f of x for all x in I, then f of c is a local maximum value of f. And if f of c is less than or equal to f of x for all x in I, then f of c is a local minimum of the value of f. Now keep in mind that the interval I is that mini interval inside, so talking about the points around it. We aren't necessarily talking about all the points on the larger interval. We're talking about the relative points or the local points around our point in concern. Looking at another example here, we have first off a function y equals f of x, and it is a continuous function, so that means there will be an absolute min and there will be an absolute max. And so we see that we have an absolute minimum here at P, and we have two shared absolute maxes at these 2 points Q and S, because those seem to be at the same y value that is the highest y value that our function reaches on this interval a to b. Well, in addition to that, we have a local minimum at R, and so in this we have two minimums, two maximums, and you could say that all of those are local. However, in this case, they are local, but they're also the absolute max at these 2 points, and one of our local minima is the absolute minimum. One thing I want you to notice in looking at this graph is look at the slope of the tangent line, and what is the slope when we reach our extrema? Well, up here, as we go over this absolute max, or even if you want to call it a relative max, we see that our slope is 0 at the top. Well, so that's going to be the same over here. Slope is 0 there, and down at the bottom in our relative min, our slope is 0. Well, that's not a coincidence. We can also look over here at the absolute minimum, and we see that, well, our slope's not 0. In fact, our derivative here is undefined because we have a corner. So our f prime at that point does not exist.